Good day. We're 118 computer science students alongside Miss Kay Solomon, a faculty from the Computer Technology Department, and we're here to present our paper titled A Confidentiality and Access Control Framework for Electronic Health Records in a Public Blockchain. So today we'll start with the topic of blockchain. According to IBM, blockchain is a shared immutable ledger that facilitates the process of recording transactions and tracking assets in a business network. This technology can record information in a distributed fashion without the need for a third party or central authority. But arguably, the most important aspect of blockchain is its security and tamper-proof nature due to the way it is designed. Once a transaction has been agreed upon based on a consensus, details of the transaction are immutable and cannot be changed by anyone. This technology is ideal for delivering information to others without needing to worry about the integrity of data. EHR, or Electronic Health Records, is a digital record of health information of a patient, which includes their past medical history, medications, allergies, immunization dates, and much more. So, storing these data in a digital manner can help improve the efficiency of sharing, making health information immediately available to authorized providers. However, due to the sensitive nature of the data, healthcare providers often have centralized systems that protects the data, but comes at a cost where the data is inaccessible to its own patients. Integrating the blockchain technology to healthcare, specifically towards EHRs, has the ability to make the sharing of medical data more accessible and still secure. Blockchain-based EHRs are implemented in a decentralized manner, which eliminates the aforementioned issues of traditional EHRs, with the additional benefit of utilizing the strengths of the blockchain technology, making sure that the security, accessibility, and integrity of data is upheld. However, since the blockchain technology is quite new, there are still some limitations in the functionality in the current state of the implementations of blockchain-based EHRs. One such limitation in functionality can cause malicious or accidental access in the health records. So with that, we have identified that the problem here is that existing blockchain frameworks have limitations on functionality when it comes to secure data sharing of electronic health records, specifically on immunization records, in terms of confidentiality and access control that could lead to several cases of patients' healthcare data being exposed, accessed, or disclosed by unauthorized users.
The implementation of the framework contains a smart contract that is used to access and interact with the blockchain and is divided into different components, namely access permission and records retrieval. The communication between these components is illustrated in the figure. The framework emphasizes confidentiality through private key cryptography to be applied on the EHRs and access control through detailed permissions and the ability to invoke and revoke said permissions. Here is a table to discuss the functions of each module and submodule. Under the Access Permission module or Permission Manager submodule that verifies that the requester is the owner of the record being asked to modify the permissions via the smart contract. The Permission Modifier submodule validates the request to change access permission and uses the smart contract to apply the invocation or revocation change as well as save the recipient's address. And the Key Manager submodule generates a key shared via the smart contract upon the update of an access permission to be used for both the encryption and decryption of a shared record when viewed by a recipient. Under the Records Retrieval module are data pooling submodule that retrieves the requested record by either the owner or recipient from the blockchain. The encryption submodule, which encrypts the retrieved record using the key generated upon the updated access permission and cryptographic algorithm set by the developer. And the decryption submodule, which decrypts the ciphered record using the provided key for the recipient for their access to the record and returns the record in plain text. Now going back to the framework architecture for a more detailed discussion, invoke and revoke of permissions as well as key generation happen in the access permission module. If the owner is the one retrieving the record, then the owner will be directly serviced by the records retrieval module. On the other hand, if the owner intends to share a record, then the process starts with an owner's request for change of permission and generates the original access permission of the requested record. The original access permission will be updated by creating a new transaction for the given access permission. The process then proceeds to the generation of an encryption key. Responsible for fetching the requested information by either the owner or recipient of being shared to is the records retrieval module. The primary functions of this component are pulling the data from the blockchain, encrypting the record according to the algorithm set, and decrypting the record for the recipient to receive, respectively. The module allows for both types of users to retrieve the record, varying mostly upon the need to securely provide a record for the intended recipient before completely accessing the said information. For the owner, a checking of access permissions for the record will first be verified, where a confirmation will result in the retrieval of the record and the owner receiving it in plain text. For recipients given access permission by the owner, the process also begins with the receiving of the recipient's request, verifying access permission, and pulling the requested record from the blockchain. The pulled plaintext record is forwarded to the encryption submodule, where it is to be ciphered with the owner's key in accordance with the specified encryption algorithm before being sent to the recipient. The recipient then, with a shared key, will have to decipher the encrypted record through the decryption submodule to receive the information again, but in plain text. The invoking or revoking of permission of a certain record for a specific address can only be initiated by the owner of the record, wherein R represents read access when access permission is invoked, and N represents no access when access permission is revoked. Once permission is invoked, as shown in the figure, a key corresponding to the chosen algorithm is created, which the recipient will need to open the shared record in readable format. If previously invoked permission of a shared record gets revoked, as shown in this figure, the key is then invalidated and removed from key storage, which leaves the past recipient no way of converting the record in readable format.
The implemented framework will make use of a private key cryptography among three known symmetric block cipher algorithms, namely AES, Triple Des, and Blowfish. These three were chosen due to their performance according to Ghosh, Parmar, Shah, and Samdami in 2018. For a brief discussion, AES is also known as the Wendell algorithm and is considered by the U.S. National Institute of Standards and Technology as the standard for symmetric key encryption. Triple Des uses the data encryption algorithm three times with a different key for encryption. Compared to other algorithms, Triple Des uses 56-bit keys instead of 64 due to the skipping of the 8th bit for parity checks bits and form three of these to form a single 168-bit key. Blowfish was known then as a good replacement for outdated algorithms like DES and IDEA. The framework implemented allows for the initialization with the chosen algorithm among the three prior to the contract deployments, and the same algorithm is going to be applied for all cryptographic functions involved such as in record encryption, decryption, and sharing. To aid in the implementation of the mentioned cryptographic algorithms for the framework, a Python library called cryptography was used. Cryptography, as stated in its document, is a package that aims to become the cryptographic standard library as it provides both high-level recipes and low-level interfaces to various known cryptographic algorithms, including symmetric ciphers, message digest, and key derivation functions. The three algorithms stated in the previous slide can be found as cryptographic primitives, which requires a certain extent of knowledge on cryptographic concepts at work.
Moving on with the EHR encryption, once a record is pulled from the blockchain, the access permission of the record retriever is checked, as shown in this figure, represented by the access permission value. 0 for neither a valid owner nor recipient, 1, if the retriever is the owner of the record, and 2, if the retriever is a valid recipient of the record. If the retriever is the owner, then the record will be directly outputted in plain text. If the retriever, however, is a recipient of the record is first encrypted so that the recipient needs to provide a key first to be able to output the record in plain text. Otherwise, the record is encrypted and is not readable. Encryption of a record checks the access permission of the user accessing the record. An access permission of O indicates that the retriever of the record is its owner, thus the record is outputted in plain text once the record ID is provided, as shown in the figure. If the retriever, on the other hand, is the recipient of a record, the key for decryption is requested and asked as input, and only upon inputting the right and valid key will the record be outputted in plain text, as shown here. Now going back to the provided three algorithms earlier, normally AES uses 128 to 256-bit keys with a block length of 128 bits, while 3DS uses 56-bit keys instead of 64. And finally, Blowfish uses a 64-bit block size. For the framework, the following sizes were chosen for each algorithm: 32 bytes for AES, 24 bytes for TripleDES, and 32 bytes for Blowfish. Along with the utilization of cryptography for EHRs upon sharing, a functionality was also created to regulate the storage of keys being used for the encryption and decryption of shared records. Keys generated are referenced by the respective key IDs, which are mostly used during transactions for queries and validations within the system. The keys are then stored externally to a binary file within the user's machine. To conclude, what was found is that with the test cases conducted, it proved how a more robust confidentiality and access control mechanism can be used to further improve the security of handling EHRs. The use of private key cryptographic algorithms shows it can enable future systems adapting this framework to be more flexible and tailoring it further to their respective organizations' compliance and regulatory requirements. With the framework's access control, it shows that it can ensure EHRs and the sensitive information are kept exclusive to authorized individuals and not easily disclosable to entities that originally should not have permission to access the said records. And finally, for our recommendations, considerations for other cryptographic algorithms are suggested because of the fast emerging technology, which also comes with recently dated threats. An evaluation of the cryptographic algorithms is also important, as to make sure that they can provide more security for the framework to add to the security provided by the blockchain technology, making such algorithms become more acclimated to the system or application that the framework will be utilized for. That would be all. Thank you.